Hello and welcome to the Unit 5 Section 3 video on triangle proportionality. So here we're going to be talking a little bit about things that you see in the field of artistry. Artists use mathematical techniques to make two-dimensional paintings appear three-dimensional. We're talking about perspective. Okay, perspective is based on the observation that faraway objects look smaller and closer objects look larger. But in order to get perspective correct, we have to use a little bit of math and make sure that our ratios and our proportions are correct. So we have the triangle proportionality theorem to help us with that. If a line is parallel to one side of a triangle and intersects the other two sides in two distinct points, then it separates these sides into segments of proportional length. So, in other words, if we have a line parallel to one of the sides of a triangle, then we can say that the two segments that end up being created along the other two sides have the same proportionality. In other words, AE, the short part, is proportional to EB, this longer part. Or you can set up that proportionality. It's the same proportionality as if you did AF to FC. So AE over EB, the short part over the long part, is equal to this short part over the long part. Okay? So let's do an example to see how this works. So we're going to find the length of CY. CY being this short part here. Well, we can set up 9 over 4, this long part to this short part, 9 over 4, equal to the long part over the short part of this one, so 10 over CY. If you cross multiply, you get 9CY equals 40, and then divide by 9, and you get CY is equal to 40 over 9, and that will not reduce. And that's all there is to it. We're just setting up the proportions and solving for what we don't know. Now we also have the converse of the triangle proportionality theorem, which goes the other way around. If we know that these segments on this side is equal to the proportionality that we have for these two segments, then we know that BC and EF, these two lines, are going to be parallel. So, in example 2, we're going to verify that MN and KL are parallel. Here we're given all of the measurements that we need. So let's see what JM to MK is. JM to MK is 42 over 21, and that is 2. So now we're going to compare this other one, JN to NL. And if we find that this is also 2, then we can say that these two lines, or these two segments, are parallel. So JN is 30, NL is 15, and yes, that is 2. So therefore, since, and this is your reasoning here, since JM over MK is equal to JN over NL, then you can say that MN is parallel to KL. That is the statement that you must make, because you have to give your reason for why they are parallel. Okay, let's move on to the two-transversal proportionality. We have a corollary that stems off of the theorem that we just talked about, the triangle proportionality theorem. We have a corollary that is a result of that theorem. If 3 or more parallel lines intersect two transversals, then they cut off the transversals proportionately. So here, AC to CE is equal to BD to DF. Okay? So we can use that in helping to figure out if the drawing of a drawing of perspective is correct. Okay. So in example 3, an artist used perspective drawing to draw guidelines to help her sketch a row of parallel trees. She then checked the drawing by measuring the distances between the trees. What is LN? So what we have to state here is we know that AK is parallel to BL, which is parallel to CM, which is parallel to DN, because these are all trees going straight up and down, so these are all going to be parallel. So therefore, all of these segments, whichever order we make a ratio, that has to be equal to the corresponding ratio from the other side. So if we want to find what LN is, that is this segment right here. So therefore we need to know what BD is. Well, we know that BD is 1.4 plus 2.2. It's BC plus CD. That's segment addition. So we get 1.4 plus 2.2, and that is going to give us 3.6. So now let's set up our proportions. KL to LN on the bottom is going to be set equal to AB to BD on the top. So let's plug in our values. KL is 2.6. LN is what we are looking for. AB is 2.4. And BD we just found is 3.6. So let's cross multiply. 2.4 times LN is equal to 3.6 times 2.6. And if you do all of this math, you end up finding that LN is equal to 3.9, but not just 3.9, 3.9 centimeters. If you're given units, you need to provide units in this. All right, let's end this section by talking about the triangle angle bisector theorem. So the previous theorems and corollary lead to the following conclusion. An angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the lengths of the other two sides. So in other words, if I bisect my angle A here and draw that bisector to the other side, I can set BD to DC equal to AB to AC. So knowing that, we're going to find RV and VT in this figure. Well, first we're going to set up our proportions. We're going to set RV to VT, which is x plus 2, to 2x plus 1. And we're going to set that equal to, well, the side that goes with x plus 2 is 10, and the side that goes with 2x plus 1 is 14. So now we're going to cross multiply and solve. So we have 14 times x plus 2 equals 10 times 2x plus 1. And we distribute on each side 14x plus 28. It's going to equal 20x plus 10. So we subtract 14x from each side, we subtract 10 from each side, and you get 18 equals 6x. So x is going to be 3 when you divide each side by 6. So now we know our value for x. We're just going to plug it in. RV is equal to x plus 2. Well, x is 3, so we got 3 plus 2, so RV is 5. VT is 2x plus 1. Well, again, x is 3, so we get 2 times 3, which is 6, plus 1 gives us 7. All right, so that finishes off this section. Coming up in the next section, we've done a couple of these in this section. You've seen a couple of application problems. The next section, we're going to get into more applications of similarity.